questions? Okay, then if you do not have any questions, we shall start the new topic. We'll talk about transportation problems. Essentially, these are linear programming problems only, but here every basic feasible solution that you are seeing, that is, it is degenerate. So, and the number of variables is too much. You will realize that. So therefore, some further insight is required, and the implementation of the simplex algorithm only one has to do, but one has to do with more care, so that it becomes very simple to implement the algorithm, and it would look more simple. So anyway, so what is transportation problem? Imagine you have a few sources. Some sources are there, and this is where things are available. At the first source you have A1 amount available, at the second source you have A2 amount available, and then at the mth source you have AM amount available, and you have few sinks. I mean, these are some demands, I mean, where the first one demands B1, the second one demands B2, and the last one demands Bn. So M sources and sinks. Okay, and what is given? It is given that summation AI total availability is equal to total demand. Fine. So idea is to transport things from here to there, but then from wherever one place to another place, you want to transport whatever unit of good you transport. The cost of transportation is also given. C12 will be per unit transportation cost from source 1 to sink 2. Okay. Similarly, from here to here, this will be CMN. So what you are seeing now, you will be given a cost matrix. Okay. M by N cost matrix. C is the cost matrix. So earlier we used to have a cost vector. Okay, because our variables were like x1, x2 up to xn. Now we have cost matrix. Okay, because we want to transport things from here to here. Okay, so then what is the problem? The problem is that transport all the goods from one side to other side, meet all the demands. Okay, just do not transport anything to just one place or from everything to one place. That is not the thing. Meet all the demands and then minimize the cost of transportation. So that is called the balanced transportation problem. The word balanced is used to mean that the total availability is equal to the total demand. Okay, this is the first one, the simpler one to talk about. Okay, so this is the picture. How do you model it? Now to model it, what you have to do, so imagine from source I, if so denote, so like the usual, in the beginning we said how to model. You first identify the variable, now xij equal to the number of units. that you take from source I to sink J. Suppose that is the number of units that you are taking, transporting. So in that case, what will be the objective function? The objective function in that case will be summation ij Cij Xij. That will be the objective function. Okay, that you can call as fx. Okay, so what is this capital X? Now capital X is the matrix of variables and X is m by n matrix only. Okay, subject to what? Now subject to the constraints. What are the constraints? So I identified the variables, I identified the objective function, I have to identify the constraints. Now what are the constraints? Now you can take A1 amount from source 1, which basically means whatever you send to B1, whatever you send to B2, whatever you send to Bn, that total must be A1. So this means x11 plus x12. X12 is the amount that goes from source 1 to sink 2, plus x1n, and that has to be equal to A1. That is A1. Okay. Similarly, you will have xm1 plus up to xmn, that has to be equal to am. So this is the A type constraints. When constraints due to the sources. Okay, these are the constraints. Similarly, at B1, whatever B1 receives from source 1, whatever it receives from source 2, and whatever it receives from source M, that total has to be B1. So this basically means x11 plus x21 plus xm1, that has to be equal to B1, and x1n plus up to xmn, that has to be equal to Bn. So this is the B type constraints, that is the sink, the constraints that are occurring due to the sinks. Okay, so these are the constraints. So that is what is written over here. Okay, minimize ij Cij Xij, summation for each I. Okay, this one is for each I. You have summation Xij equal to Ai. So these are the A type constraints, and this is for each j, summation over all I Xij is equal to Bj, and of course Xij are greater than equal to 0. Okay, so that's how you model. Fine. Now suppose I want to write the SLPP. Let me take okay, before that, here is a simple this is very simple. Here is something. Let me say, take a simple example. You have this is like what do you say, uniform distribution or something like that. Okay, so let me simply not dot dot dot, but simply let me have 10, 20, 30, 3 places only. Okay, there are 3 places of availability, and then I have 5, 15 and 40. These are the demands. Okay, so I want to make a transportation. So what is a solution? Now solution is the matrix M, a matrix X of Xij, right? That will give you some distribution. For example, a solution over here would be some distribution from here to here, here to here, I mean everywhere, this thing. Now to show that there is actually some distribution, there are many ways to do. I mean, just take the first one, the greedy type of this, first finish this, so that is 5 units. Whatever remains, it goes there, so that is 5 units. Then from here, whatever is remaining, you try to finish the second one by one. So meet the demands one by one. That not the greedy one, but meet the demands one by one. So go on meeting the demands one by one. So that will be 10. What remains is 10 over here, and then you go and meet. That will be 30. The other one would be like something like this. So what you do, whatever 10 amount it has, it will distribute it proportionately. So totally is like 60. So you take 10 by 60. So give 5 units to, I mean, divide 10 into 60 parts. Okay. And then give 5 parts to 5, 15 parts to here, 40 parts to here. Similarly, take 20 and then make 60 parts. Okay. And then give 5 parts, send 5 parts to the top, then 15 parts here and the remaining parts here, and do the same thing with 30. So see, if everybody is distributing proportionately, that will also be a feasible solution. So these are feasible solutions. That basically means the feasible set is non-empty. Okay, so that is what this lemma says. So consider the BTP in P, then the set of feasible solutions is always non-empty. Here I have done the distribution in ratio part. You can also give others, that is no problem. So in any case, that is what the thing is. Okay. So here is something that I want to do. So here I again point out, I appeal that you just do not see, you try to observe what is happening. Okay, your observations will help you. Okay, so let's see. I am taking a 2 by 3 BTP and I am writing the constants, and I am interested in writing the SLPP. So 2 by 3 BTP, if you want to imagine the picture, you imagine the picture. This is A1, this is A2, and this is B1, B2, B3. Okay, write down the constraints. So I write down the constraints. What are the constraints? Now x11 plus x12. X11 is whatever that goes from a source 1 to sink 1. X12 source 1 to sink 2 plus source 1 to sink 3. That total must be A1. Again, since I am writing for sources, source 2 to sink 1, source 2 to sink 2, source 2 to sink 3, that total must be the total availability at source 2. Then now sink 1, whatever it is receiving from source 1 plus whatever it is receiving from source 2, that must be the total demand. Then sink 2, whatever it is receiving from source 1, whatever it is receiving from source 2, that must be the total demand. And similarly, x13 plus x23 equal to B3. Acha. So that is fine, no problem. I want to write down the SLPP. Objective function, I know it is like summation Cij Xij as soon as the Cij is given. But I want to write down the coefficient matrix A. So I want to write down the coefficient matrix A. So I will write down the variables x11, x12. This is the way I am writing. X13, then x21, x22, x23. The lexicographic order. That is the way. Dictionary order, you might also be knowing in that way. So what is the first? So this is the matrix A. It will have two parts. One, the first constraint. What is the first constraint? Now 1, 1, 1. Acha, here it is the matrix, and then the B vector. That also I have to write 1, 1, 1, and this is A1 0, 0, 0. That's okay. Next, now x21, x22, x23, that means 0, 0, 0, 1, 1, 1, and that is A2. Writing down this x I have written. Actually, x you should write here only. You can write x here only and put an equality here. No problem. Okay, so that finishes the equations due to the rows. Now I have columns. What is that? X11 plus x21, so that is 1, 0, 0, 1, 0, 0, and that is B1. Then 0, 1, 0, 0, 1, 0, that is x12 plus x22, it is B2. And then 0, 0, 1, 0, 0, 1, that is B3. Okay, so what do I have now? I have one equation for each source and sink. So total I will have 5 equations. So that's why. So size of the matrix, now m plus n rows, and how many columns? The number of variables, that is mn columns. Okay, that is what it is. So this matrix has two parts. Roughly the AI part and the BJ part. I mean the rows due to the sources, the rows that you have written due to the sinks, essentially. Okay. Notice the column for x23, that is this column. The column for x23. It has two parts. Okay. What is the AI part? That is the source part of column for x23. Now actually if you are seeing the column for x23, then the column for x23 looks like E2, this much is E2, and then E3. You check x11, well, this is the column x11. What is the column that you have written? Column below x11, this is E1, and this is E1. These sizes of E1 will depend on how many sources are there, how many sinks are there. That is it. But it is E1 by E1. By means, I mean line. Okay. So what you observe from here, a general, if you are looking at the column below Xij, then the column below Xij will look like Ei and then Ej. This Ei size is the number of sources. The bottom Ej size is the number of sinks, the vector size. Okay, but the column, that is what you are getting. And then the constant matrix is all the AIs, then after that BJs are written. That's how. So that is the coefficient matrix for the SLPP. Okay. So that we have written formally over here. We can write the problem P. By saying problem P, I mean that BTP, the general M by N BTP, in the following way. It is minimize C transpose X, where C I have written in the lexicographic order, X is also written in the lexicographic order, the same, and B like B is A1, A2, AM, and then B1, B2, Bn, that way. And each column below Xij takes the form EI divided by EJ, not divided by line. Okay. So this is the Cij column. And what else to observe? The first block that you are seeing over here, okay, is like 1, 1, 1, rest of them 0, and at the bottom you have an identity. If you still want to see, you have an identity over here. This one is identity. This one is the same identity. This one is the same identity. Here you have all ones on the top. Here you have all ones at the bottom. Here you have all ones at this. Okay. So this is simply because the first one is for the sync 1. This is for sync 2. So you will start with x21 plus x22 up to x2n. And nowhere else you require anything. So that is why it is there. Okay. So this is the structure of the matrix. And the thing is that there are so many. So if I give some 10 by 10 transportation problem, your number of variables will be 100. I mean, that's too many. A lot of this thing. Anyway, so we shall call it a constraint matrix. Actually, the actual name is constraint matrix. I have a habit of saying coefficient matrix. Okay. So please do not confuse. It's the constraint matrix only. Now, if you want to apply the simplex method, or you want to analyze whether simplex method can be applied, and the first thing you want to know is what is the rank. You try to guess what is the rank over here. One thing is easy to guess. You take the sum of the first m many rows, that is the rows due to the sources, and then the sum of the rows due to the sinks, and you will get the same result. So therefore, it automatically says that this one has rows linearly dependent. Okay. Not only that, what else you see? Now you also see the following. If I write R1 as, right now, suppose, allow me to write this as R1 as, by writing R1, I mean row 1. Okay. So what you are seeing now, I am seeing that R1 plus R2 up to Rm. Sorry, not this R, but Rm. Okay. That is equal to that is the rows due to the sources is equal to R m plus 1 the next rows up to row m plus n, and that is equal to 1 1 1 1 1 1 1 1 1. That's the equality. And therefore what I am saying, I can write R1 as a linear combination of the rest of the rows. Similarly, I can write any row as a linear combination of the other rows. So what I am seeing that out of all these rows, these rows are linearly dependent, and I can delete any row of my choice, and that will not decrease the rank, because every row, any of the rows, you take any one, it can be written as a linear combination of the remaining. So throwing away that row will not reduce the rank. Fine. Fine. But the rank is actually equal to m plus n minus 1. It says, basically it says that much only. You can delete any row, whatever remains, these rows are linearly independent. Anyway, so to prove this, there like we can give three different arguments. Two I will give now. The third one in due time, maybe in the next class or sometime when it comes. Right now I will give one. Let's see. See, if I want to say that the rank is m plus n minus 1, it is enough for me to show that there are these many linearly independent columns. That will do. Now I have targeted linearly independent columns. What am I targeting? Now I am targeting column 1. Okay. So column 1 means it is corresponding to which variable? So I will be writing C, instead of column 1 writing as C1, I would be writing C11. C11 stands for the column corresponding to the variable X11, that is the first column. Okay. So C11, notice this one, notice in the matrix itself, C11, C12, okay, go up to C1n, that is these columns. They are linearly independent or not? They are independent. At the bottom I have identity, na? So they will be linearly independent. Okay. Okay. Then what I pick? I pick C21, that is the first column. So that is this one. This has a 1 at the second place, from the top at the second place. Okay. Then I pick C31, that will have a 1 at the third place. Okay. And likewise I will pick CM1. Okay, so that is this one, this one, this one. So all these columns are linearly independent. The first n are linearly independent because of the bottom identity that you are getting. And C21 is independent of, does not belong to the span of the first n, because C21 has a 1 at a place, the second place, and in the first n vectors the second place has been 0. So therefore C21 does not belong to the span of the first n. Okay, so therefore that makes this whole thing linearly independent, that is C11, C12, C1n up to C21 linearly independent. Fine. Now notice that C11, C12, C1n, C21, all of them have zeros at the third place from the top. And C31 is a vector that has a 1 at the third place. C31 is E3 by E1. You remember that. It is not drawn over here. So that is why. And therefore C31 will not belong to the span of the previous. And hence its inclusion will still keep the set linearly independent. And the argument continues. Okay. So how many vectors I have obtained from here? Now I have obtained m plus n minus 1, these many. Okay, so I saw that there are m plus n minus 1 linearly independent columns in this matrix. Therefore, a rank of this matrix has to be greater than equal to m plus n minus 1. But then we already have shown that rank of this matrix is less than equal to m plus n minus 1, because there are m plus n many rows and one of them is like a linear combination of the others. So it follows that rank is equal to m plus n minus 1. The argument that I have written over here is a little different. I made use of the structures. Okay, it is a little different means it is kind of our uh, first semester linear algebra style. I took, suppose alpha 1 times this plus alpha 2 times this plus alpha n times this is equal to 0. Then I showed that alpha 1, alpha 2, alpha n that is equal to 0. Okay, so I didn't tell the span argument that I am selecting the general style of argument, that is the I mean the linear independent linear proving linear independence by putting your argument using that span argument. So that I have not written over here, but that is okay. They essentially these are the same. There is another style of argument that you can that I have written as an exercise. This is the very old style of argument. This is the classical one. That means this is the one that you can find if you take any textbook, old textbook, you will find this. Okay. Anyway, questions till now? Okay, no problem. And then we'll talk about, so this is about the rank. So rank is number of rows minus 1. Fine. Fine enough. I don't have a problem. Next, the problem table. So how do I write the problem table? This is kind of two-dimensional x1, 1, x1, 2, m many variables. Like the variables are they themselves present as matrices. So how do I write? So this is the transportation array is an efficient way of writing, representing a problem, transportation problem. Now the transportation array would be written like this. So you will write, if there are m many sources and n number of sinks, then you will have m by n table. Okay, so m many rows. So suppose that I have 3 sources and 4 sinks, then I will have this kind of a table. So then I understand that this first table is for x11. Okay, this is for x12, this one is for x14, and I can simply write if the cost of transportation from source 1 to sink 1 is 5 per unit transportation, then you write 5. 5 means writing a 5 there means cost of transportation along that road is 5. Okay, 5, 2, 1, whatever you can write that way. And also you can write A1 over here. Suppose the total availability is 50, then you write 50. That means from source 1 has 50 units of goods. It can go to sink 1, sink 2, sink 3, sink 4. Cost of transportation is given like this, whatever it is. So that is the way. Similarly, a B1, B2, B3, B4, those are the demands at the sinks. So this is the transportation array is a very, very easy and effective way of representing the transportation problem. Okay, and therefore if we do our steps on this table, it can be done very easily. Okay, and it is very easily understandable. So before that, let me simply write the transportation problem as an example here. So a company has plants in 3 cities, Guwahati, Shillong and Jorhat. Okay, these are 3 places in Assam only. Okay, with capacities of something production 200, 250 and 300, and it has signed contracts to supply goods to 4 different mills, and the contracts are for like 150, 200, 250 and 150. Okay, and this is per month. Okay, fine. And then the cost of transportation per unit. So here the unit is in ton. So is given in this matrix. Okay, that is from Guwahati to, if you want to transport 1 ton of good to mill 1, then you have to give 1.5. The cost is 1.5. You want to transport from Guwahati to mill 2, then it is 2.5. To mill 3 it is 2, to mill 4 it is 1.1, like that. Okay, so now the question is, write the transportation array. Well, you can easily write down the transportation array. You do not have to watch me writing it, but I understand that it is 3 by 4, 3 sources, 4 sinks. Okay, so I will have a 3 by 4 table. Okay, and then variables are of course x11, x12, x13. I don't want to write that. With my understanding, that is the variable. So I will write simply 2.5 to 1.1, and similarly 2.0, 3.0, 1.5. You write it at this corner. Okay, when we will start writing the values of the variables, we will use the top left corner. 1.2. Do a bit bigger table so that your writings would be easily visible. This one is 1.8, 3.2, 1.8 and 1.0. That is fine. And you have to write the total availability. Total availability at this one is sorry, not 1.1. What is the total availability? Sorry, 200. 200. Total availability 250, and total availability here is 200, 300. That is the total availability. Similarly, what is the total demand at mill 1? Mill 1 total demand is 150. Next one is 200. Next one's demand is 250, and next one's demand is again 150. So that is my transportation array. So if you want, you can write your x11 and x12 like that if you want to write that way. So normally when I write, I put a double line over here, put a double line over here. Okay, double line over here, and extend this as a table. Okay, I do not put anything here, nothing over here. Okay, this is how it is. Fine. Okay. Okay. So when I say 3x4 transportation problem, it means 3 sources, 4 sinks. Fine. So in a 3x4 transportation problem, the matrix A, this is the constraint matrix A, has size dash by dash. So this will have size. How many constraints? Now remember, one constraint for each source and one constraint for each sink. So total will be 7 rows. How many variables? Mn variables. 7 by 12. Okay. Fine. Next. Which row or column of the transportation array correspond to the rows of A? For example, I am looking at the third row of the transportation array. Okay, I am looking. What are you looking at? Now I am looking at the 3x4 transportation problem. Okay, and I am looking at the third row. So the transportation problem, you can, for example, you can take it here. Take this one here. This is 3x4 only. So I am looking at the third row. The third row of the transportation array. What row? So it gives you a constraint. Okay. So therefore, it should be corresponding to a particular row of the constraint matrix. Which row of constraint matrix does it represent? Now this one will represent the third row of the constraint matrix itself. Okay, this means, this one means x31 plus x32, because it is 3x4, huh? Plus x33 plus x34 is equal to A3, and that appears, if you are looking at the matrix, that will appear in the third row of the matrix itself. Okay, somewhere if you have observed the matrix carefully, see the first one is corresponding to x11 plus x12 plus x1n equal to A1. Second one is x21, x22 up to x2n, and third one is that. Okay, fine, that you have. The next question, the second column of the transportation array. The second column of the transportation array is this one. What does it tell? Now it tells x12 plus x22 plus x32 is equal to 200. Right now. So there it will be B2. What does it tell? Now it tells x12 plus x22 plus x32 is equal to B2. So what is, by which row in the constraint matrix is this represented? Now look, if I remember the constraint matrix, the constraint matrix has the first top m many rows are for actually the sources. Top row is for source 1, second top row is for source 2, then like that the mth row is for source m. Then what happens? Now then the sinks start. Then sink 1, sink 2, and this one is for sink 2. Okay, and since it is a 3x4, the first 3 rows are gone for sources. This is 3 rows. Okay, and this is coming in number 2, so this one's number must be 5. Okay, the 3 rows are gone, and then one more row gone for the sync 1 for writing the constraint for sync 1. This is for constraint 2. So this is number 5. Okay, so this is 5th. Okay, fine. One more thing we need to observe. Suppose that I have a 4x6 matrix, something written, no problem, and I have highlighted the 3,5 entry. Okay, and that entry I want to bring by doing the some row permutation and column permutations. I want to bring to the 1/1th corner, that is the top left corner. So what permutation matrix? I want to multiply permutation matrix. If this matrix is A, I want to multiply a permutation matrix and a permutation matrix over here. Okay, a permutation matrix and a permutation matrix, so that in the result I want to have A13 at the top left corner. Now give some permutation matrix that will achieve my target. Well, the idea is that here you want to take the third row to the top row. Therefore, what you are going to do, you are going to take the permutation matrix here. Acha, if this is the P is the permutation matrix, if P is the permutation matrix that I want to multiply with A, what will be the size of P? The size of P will be 4x4. Permutation matrices are square matrices. Okay, and since I am going to multiply this with this, so it will be 4x4. So what permutation matrix I am going to take? Now you first take one, the identity matrix you first take, and then realize that I want to take the third row to the first row. So all you have to do is you have to interchange the first one and the third one. Okay, you erase them, make them zeros, and put one over here and one over here. So then the matrix is like this. That is what, starting from the identity matrix, I want third row and first row interchanged. So that is what I do. So this is a permutation matrix. You must be knowing many things about permutation matrices. Permutation matrices are coming from permutations only. Okay, permutations means what? Now it's a bijection from a set of n elements to itself. Permutations, if you have taken your group theory, a little bit of group theory, you already know permutations can be written like 1 to up to n, and then any arrangement of 1 to up to n, something like, you can write it in many different ways. Permutation sigma, the permutations form a group, and a permutation matrix is invertible. In fact, if you take P and P transpose, P transpose is identity. Many properties of the permutation matrices. And if you remember, a few days back I told that not many people will talk to you about, tell you that when they are talking about permutation matrices. The permutation matrices are precisely the vertices of the polytope of the set of the convex set of doubly stochastic matrices. Okay, so that we have observed. So here third row goes to the first row, so I want to multiply it with this. And here what size of matrix I will take? Now there are 6, so I will be taking 6 by 6. And what do I have to do? Now I have to take the fifth column to the first column. So what you will be doing? Now you will be taking the identity matrix, then first and fifth make 0, and then put ones in those places, like so: 0, 0, 0, 0, 1, 0. That is how it is. 0, 1, 0, 0, 0, 0. So the second row as such: 0, 0, 1, 0, 0, 0. Third row as such: 0, 0, 0, 1, 0, 0. Fourth row as such. Fifth row 1, 0, 0, 0, 0, 0. Sixth row as such: 0, 0, 0, 0, 0, 1. Okay, so what I did, now I have taken identity matrix, then made this entry 0, made this entry 0, and then changed 1, 1 over here. That is the permutation matrix that will interchange the fifth column to the first column. Okay, so essentially what is this? Now this is identity minus E11. E11 is the matrix that has 1/1th entry 1, rest of the entry 0, minus E55. I made fifth entry also 0, plus E51 plus E15. So that is the matrix. Similarly, it is this one, identity minus E33. So that is what it is. Okay, we'll talk about lower triangular basis. We'll show that a basis over for a BTP, a basis for a BTP is lower triangular. That we'll talk. See, what is a lower triangular matrix? A lower triangular matrix is that, I mean, normally people talk in square matrices, but given any rectangular matrix, you can talk about AII, okay, that as your diagonal, okay, and lower triangular means above that diagonal whatever entries are there, they have to be zeros. Okay, so for example, if I have a so here, for example, in the top, okay, let me write it here. So if I am talking about a lower triangular matrix and I have a 3/4 matrix, so you have one entry, this can be anything, no problem, and this has to be 0, 3/4, huh? And then this can be anything, this can be anything, but this has to be zeros. 3/4 I have, so this can be anything, this can be anything, this can be anything, this has to be 0. Okay, that's how it is. Anything above that, so that has to be 0. Okay, so anything above. And let me tell one thing. No, I do not force, actually. I may not force whether I will require the last few entries. Yeah. So it is like A11 is fine, but A12, A13, A14, everything else will be 0. So that's how it is. Yeah, that's okay. No problem. So that will be lower triangular. So each Aij such that if j gets bigger than I, so that is it. It has to be 0. Okay. And then there is a lemma that we'll need to prove that a little later. That proof will take some time, so I cannot do that here. But let me ask one simple question. So I will be stopping over here. I will start from lower triangular basis from the next class. But let me ask a question over here. Something like this. Imagine that you had a eight by 10 matrix. Okay, you can talk to me over this. So assume that you had one matrix capital X, which is 8 by 10. Fine. You have written, okay, you have written one matrix 8 by 10. Some entries you have written. Then when you go out, you went out for maybe 2-3 minutes or something. Then your friend comes and then he has chosen some 3 rows of his choice. He selected some 3 rows of his choice. And whatever entries were there, he just changed the signs, okay, of each element in those rows. If there was one element -5, he would made it +5. If there was one element 4, he would made it -4. Just changed the signs of entries on those rows without telling you. Okay. And then unfortunately, he went out and one more friend came. Okay. And then he selected 3 columns of his choice and did the same thing. Changed the signs of each entry in those columns. And then he left. Okay. The original matrix that you had written had rank 6. What would be the rank of the final matrix? Can you justify that the final matrix has rank 6 also? Or can it go higher? Okay, no problem. You don't have to answer me. You think about it. We'll talk about it in the next class.
Excuse me, sir?
Yes.
I think it should still be rank 6.
Yes, it will be of rank 6. And
Because,
the fact, yes, you tell, please.
If you consider, say, the first friend transform the matrix from X to Y and the second from Y to Z, then all I want to show is that if I change say a number of columns or a number of rows, the sign of those, then that maintains the rank. So the transformation is just twice of that same transformation. So what I can say is if the initial rank was 6, then there are 6 rows that are linearly independent. And so changing the sign does not make them linearly dependent, because then that would imply that they were originally linearly dependent. So Y is rank 6, and so Z also has rank 6.
Right. The proper justification would be that this change can be achieved by multiplying an invertible matrix from left. The changing the signs of the rows will be as good as, suppose you have changed the signs of the first 3 rows and it is a 8 by 8 matrix, so you will be multiplying the 8 by 8 identity matrix, and if you are changing the first 3 rows, keep the first 3 -1 all the other are 1. Okay, all the rest are 1. So that, okay, so basically what I am saying, if you have this matrix and you multiply this by something like, let me simply say -1 -1 1 1, If I do that, what this -1 does, they will change the signs of the first two rows, and the rest of the things they will keep as such. So changing the signs of few rows means multiplying the matrix by an invertible matrix from left, and similarly from column, from right. And as you know, multiplication by an invertible matrix does not change the rank. Okay, we stop here.